This section is to discuss D'Alembert's solution of the wave equation. So we will attack the wave equation again. And here we will obtain a general solution of the wave equation. Okay. Right, so let me write down the wave equation. Okay, so this time, we will not restrict ourselves to a finite interval of the space. So here x is just the whole real line. And the time still begin at 0. Okay, so begin at 0. So we are talking about the situation. Okay. And so I have to underline here. Now, so for such a wave equation, the general solution can be immediately obtained by transforming the original xt coordinate system to a suitable we call VW coordinate system. Okay. As follows. Actually, in the recommended exercise, I put an additional problem, right? And also we have a quiz to illustrate that if we do a proper coordinate transformation, we can transform the original PDE to a much more easier, simpler PDE to solve, right? So this is the idea. And here, we illustrate the similar idea to wave equation. Okay. And you can see that the coordinate transformation is quite similar to that we introduced in the quiz problem, right? So W is x minus Cp, and here C is the velocity appeared in the wave equation. Okay, right? So now you consider such a coordinate transformation. And actually, it is called the linear transformation. Okay? And the inverse coordinate transformation it's quite easy that x can be expressed as a function of v and w. So x is just the half of the sum of v and w, and the t is just the half of the difference. All right, and also divided by c. Okay, so we have the coordinate transformation and the inverse coordinate transformation. They are very simple. Okay, and now we write down some data. Okay, for the v, the partial derivative of the v function relative to x is equal to 1, and vt is equal to c. For w, the partial derivative of w with respect to x is equal to 1, and wt is minus c. Okay, so this is the first partial derivative, right, for v and w. How about the second partial derivative? Well, we find that they are all equal to 0. Okay, so v at x equal to 0, vtt equal to 0, w xx equal to 0, wtt equal to 0. Okay, so we know that they are all zeros. Okay, now define. So now we have coordinate transformation, right? So define u tilde of vw is equal to the original u, but we take the coordinate transformation. So we define the new function u tilde, and the independent variable becomes to v and w. Okay, because that x and t can be expressed by v and w. Okay, so we define this new function. Then of course, u can be obtained from u tilde. Okay, so then we have uxt x tilde is equal to u tilde v xt wx. Okay, so this is the situation. So that if we have can solve obtain u tilde, then by the substitution we can obtain u again, right? So we have such a relationship. Now with the coordinate transformation, we would like to transform the original wave equation. Okay, here the independent variables are x and t. So we want to transform this equation into another equation governing the u tilde, and the independent variable becomes to v w. Okay, so for this purpose, we know ut. Okay, so for ut here, okay, by chain rule, you can see this is v, right? The first order partial derivative v and the vt here plus u tilde w and wt. Okay, so this is just by chain rule. Right, and we know what is vt, what is wt. Okay, so v here, w here. So we have c and u tilde v minus u tilde w. Okay, so we can write it down. How about utt? Right, because it appears here, right? It's the second partial derivative of u with respect to t. So utt here, so that again we know the partial derivative. This one is also a function of the v and w, and then because v and w are function of x and t, so this one actually is a function of x and t, and so we have c here. Okay, for first one, this one, we have u tilde v and the vt again, right? And so plus u tilde v the w sub t. Okay, this one minus the 0 u w v V delta V minus W of T. Okay? Right. Also by chain rule. And then we can do the substitution again. So, so this is equal to C squared. Okay. And the U delta VV minus 2. So VW, okay, so this is C, this is minus C, so we have 2 U delta VW plus U delta W, okay? So we just do the substitution because we know what is Vt, Vx, V sub x, W sub x, W sub t. We don't know this, so just do the substitution. Okay, since this is for positive derivative with respect to t, now the positive derivative of u with respect to x comes to u delta Vx plus u delta W of x. Okay, and this is equal to because Vx equal 1, Wx equal 1, so we have uv delta plus u W2. Okay, and then we do the positive derivative again with respect to x, and so so here we have u v, okay, and the v Vx plus u x, okay, plus here Vx plus x again, okay, and so all the first part derivative equal to 1, and so we have u v good plus 2 u. Okay, so we have all this data here. And now we put everything here. Okay, so now we have c squared here, right? And u v minus 2 u v w, okay, equal to c squared here u v plus 2 u v w plus u w2. Okay. Okay, just by substitution, so we cancel them, and we cancel this one and this one. So finally, we have u v w is 0. Very simple partial differential equation. Right? Very simple, right? And we know how to solve it. Okay, so this implies that so a general solution it's u delta Vw equal to phi u plus c W. Okay? So we have that. Because we can do the integration twice, right? So we can do that. So this is a general solution. Where phi and the c, okay, are arbitrary. Okay, so they are arbitrary differentiable. Arbitrary differentiable function. Differentiable functions. Okay, okay, because that v and w for here, because x can be any real number, even though c will be non-negative, but the sum here or the difference here, all right, for here will render v and w to be belong to R, right? Can be any real numbers. So for this reason, we ask phi and c are arbitrary functions of R. And it is differentiable because that we have to make sure that this has it has the mixed second order positive derivatives. So if we take the derivative relative to v, then this one must be differentiable. Or if we take the positive derivative with relative to w, then this must be differentiable. Okay, so this is the reason why we require phi and c to be differentiable. Okay, but they can be arbitrary differentiable ones. Okay, so up to here, do you have any questions about that? Right. And the reason why we select these four numbers, actually number discovered this transformation. Okay? And found out that if we select such a coordinate transformation, when we do the same thing up here, we can cancel all the second order positive derivatives except the mixed type. Okay, except the mixed type. So that's why we have this simple PDE, and then we can get a general solution. Okay, so now we have a utility already, right? And we have a general solution. And so we now obtain our original U by using this formula. So so that we have a general solution of the wave equation uxt is equal to u tilde vxt wxt. So this is y vxt plus the c wxt. Okay, this is our. And what is vxt? Vxt is that is y x plus ct c x minus ct. So once again, the general solution consists is a superposition of two traveling waves. Okay, one is this wave going to the negative direction. The other is a traveling wave going to the positive direction. Okay, and the wave front is for the negative going traveling wave is phi. This is the wave front. Okay. And for the positive going traveling wave, the wave front is c. Okay. So they may have different wave fronts, right, for the two traveling waves. Okay. All right. And so which is known as Lambert solution. of the wave equation. Okay, and here, furthermore, we assume that phi and c are twice differentiable. The reason is that in the wave equation, we have to take the second partial derivative, right, for u. Alright, and for that to be possible, even only if that phi is twice differentiable and c is twice differentiable. Okay, so for our purpose, that we will assume that both functions are differentiable, twice differentiable. So any questions? Okay, now we get the general solution here because we do not restrict the space, right? We just say, okay, the x can be any points, right, in the real line. But our original wave equation comes from the vibrating string, right? And the vibrating string is that we have a finite length of the string and fasten both ends. So how can we adjust our general solution to get a so-called unique solution, right? Because we have boundary condition here. So assume that the following initial condition are given. Alright, so u of x is 0 is equal to f star x. Okay, and ut of x is 0 equal to g star x. Right, for all x in R. So suppose we have initial condition. Okay, so first of all, we impose the initial condition here, and so we have that the function u at time 0 is equal to f star x, and the initial velocity, right, it's at time 0 is g of star x. Okay? So you first put the initial condition. Okay, so and then we will put boundary condition in there, right? So but here we put initial condition, and for initial condition we don't need to. We can say that we have the values for all the x in the R here. So now since UTXE, alright, so the first partial derivative is C phi prime x plus CP minus C CR is prime x minus CP. Okay? So the two initial conditions. Okay. I haven't put the numbers. So, okay. Let me say this is 12.4.2. The wave equation has the equation number 12.4.1. I forgot to put on the wave equation at the beginning of the section. So if you still write your notes. Please put 12.4.1, the equation number, to the web page. Okay, so okay, so this is our initial condition. So this is 12.4.3. So the two initial conditions in 12.4.3, okay, implies that, right? So imply that, okay, u x0 equal to 5 over x. So when t equal to 0, we have 5x plus the cx. Alright, and this is equal to f star x. For ut x0, we have c prime x minus c plus c prime x equal to g star x. Okay, so we have these two, right? We have, and now we have two equations to determine the phi and the c. Right? So we have two equations here from the two initial condition. And two initial will be sufficient because our space, the one-dimensional space right here, we don't have end, right? So we don't have boundary. Okay, so we extract from minus infinity to infinity. We only have the boundary for the time, the initial time. Yeah. So that's why we have to do that, because we have two unknown arbitrary functions to determine. So now we can what can we do? This is 12.4.4. This is 12.4.5 for here. Now before we solve the phi and the c, we do the integration relative to x, right? Because this is the derivatives. So when we do the integration, so we're integrating 12.4.5. Okay, so we have what we have, 5x minus cx equal to 1 over c, x is 0, g star x dx, okay, plus 5x is 0 minus c x is 0. Okay, so we just select any x 0, right? Because we want to integrate from x0 to x. Okay, so this is the initial value, the constant we have. Okay, so now we have that. Okay. So now we have this expression, and then so we combine 12.4.4 to this one. So immediately combine by 12.4.4 we have 5x. Okay, it's 1/2 f star x plus 1 over 2c x is 0, g star x dx plus 1/2 of 5x is 0 minus 2c x is 0. Okay, so this is 5x. How about 2cx? 2cx is 1/2 over f star x minus 1 over 2c, and the integral from x0 to x and g star s dx minus 1/2 5x is 0 minus c is 0. Okay, so now basically we can write down the two functions. But interesting, okay, we have something left over, right? Because it seems that we cannot determine phi and the c yet, even though we know f star and g star because of here, because of this constant. It seems like that. Well, but substituting okay, 5x and cx into the Lambert solution. Okay, in here, 7.4.2. So when we do the substitution, we have okay, so when we do the substitution, we have okay, u of xt okay, equal to, so we do the substitution, right? So this 1/2 f star here is x minus cp plus f star x plus cp. Okay, so this is for x plus cp and x minus cp here. Okay, so this part. And now here. Okay, so when we add together, and so what can we have is that is 1/2c, okay, and x0, but x is going to be x minus plus cp and the g star x here, right? Plus this one, okay? It's a constant. And but when you add together, these two constants cancel, right? Okay, they cancel. So now you have minus. So here is x minus cp, x0, g star x dx. Okay, because the constant cancel with each other. Okay, so now because at this point we are a little bit embarrassed because we have this constant there, right? But once we put back to our the Lambert solutions, we find these two cancel each other, and so we have this one, okay, and then right, and then interestingly, we can combine the difference together, right? So this equation is because minus sign, you can change the order of the integration limit, right? So it seems like you integrate from x minus ct go to x0, and from x0 go to x plus ct. So the thing is that you get x plus cp, x minus cp, g star x dx here. So x0 disappears. You don't need x0. Okay. Okay, so we have done, right? We have a unique solution because f star and g star are specified by the initial conditions, right? And the solution already is described by using the f star and the g star. So this is the unique solution. So it says that we can determine a unique solution by using two initial conditions. Okay, by using two initial conditions here. Okay, do you have any questions up to this point? Yes, please. Okay. Because when x equals x0, this is 0, right? Yeah. When you put x0 here, this should be equal to this point because the equal is equal to 0. It's fine. Other questions? Okay, good. Now we will back to our diverting string problem. But now, suppose that two boundary conditions are imposed. Okay, at the point x equals 0 and the point x equals L. Okay, so we are required that this is 0 and ULP is 0 for all t greater than 0. So, okay, suppose we have two boundary conditions here. Then we must, okay, so we must have, right, 0. So we have to put, because now we have, this is our unique solution, right? Okay, and so we have this one, f star minus Cp plus f star Cp plus 1 over 2c Cp minus Cp g star x dx, right? So this is 0. Okay, this must be true for all p greater than equal to 0. This must be true. Okay, so this is an identity. And also at L, so we must have 1 to f star L minus Cp plus f star L plus Cp plus 1 over 2c L plus Cp L minus Cp and g star x dx. Alright, so we have these two identity. And this one, it must be true for all t greater than equal to 0. Okay? Now, in section 12.3, actually the previous section, the initial condition, okay, are specified. Okay, it's specified only on the interval from 0 to L. Okay, so we just specify x is 0 equal to f of x and UP x is 0 equal to g x. I'm sorry. That. So we just specify where f is 0, fl equal to 0, and g 0 equal to g L equal to 0. Okay? Because we fasten to ends. So both ends never diffraction, right? Just stay there at 0. So we have the data, okay, as required by the boundary condition. Okay. All right. So we may, in that problem, we may regard f and g, okay, to be in the half range, okay, of bad periodic functions f star and g star respectively. Okay, so actually, so we, as before, right? That we regard f star, the relationship between f and psi is that f is in a half range of an R-graph functions. Means that we can construct f star from f, and we can construct g star from g, right? Okay, no problem with that. So we now in this situation, all right. So now we have two identities here. So this is 12.4.7. Okay. Okay, so in this situation, we show that okay, the two conditions are in here in 12.4.7. Are true. Okay. For this f star and the g star. Okay. So now f star and g star are constructed from f and g. Okay, from f and g. So f star and g star are periodic function with period. All right, 2L. Okay, so. Okay. Now, since both f star and the g star are periodic with a period to L, so we have, interestingly, minus p plus f star Cp is equal to 0. So we know this is 0. Okay, this is 0. And the integral, because G star is odd, so the integral is 0 too. Okay, so this is 0 immediately from the property that f star and g star are periodic functions with a period 2L. Okay, so we get that. And for this one, also, and f star L minus Cp plus f star L plus Cp. Alright, this is equal to f star minus L minus Cp, because this is periodic with 2L. So we minus 2L, right? Get the same value. So we have that plus f star L plus Cp. So this is, and because it's R, so we have this one L plus Cp. So it's 0. Okay? So we prove this is 0 for all t. This is 0. And similarly, L plus Ct, L minus Ct, G star x ds. Okay? Alright, so so we can do this that we have from Ct minus Ct G star S plus L ds. Okay? By change of variable. Okay? So we can, this one is equal to this one. Okay? And this is 0 since, alright? Since we consider this as a function of, so we can think about that this is h of x, okay? So we think about things h of minus x, okay? We prove h of x is r. H minus x is equal to g star minus x plus L, okay? And because g star is periodic with period to L, so we minus to L, right? We get the same thing, okay? Right? And then, so this is equal to, and also g star is r, so we have minus g star s plus L, okay? And by definition, g star s plus L is hs, so it's minus h of x. And we're done. So we show h function is r function. Okay? So this is, and so it's 0. 2. Okay, so we prove that if f star and g star are the periodic function with period 2L, then this is 0, this is 0, this is 0, this is 0. Okay? So the identity, these two identities are satisfied. Okay? And we're done. So this is the Limbert's solutions. Okay, so we find a general solution for the wave equation for x in the whole real line. Okay, and we get the general solution. And also we can find the unique solution if we impose two initial conditions. Okay. And from the initial conditions, we actually are able to find out the solution here. So this is the unique solution determined by the two initial conditions here, the f star and g star. Okay. And when we go back to our problem of the vibrating string, we impose, actually we specify the initial condition over this finite intervals only. Okay? So we may regard the f star and g star are periodic functions, okay? And with period to L, so that they can be constructed from f and g uniquely, okay? So the construction uniquely. And so the boundary condition, these two boundary condition has been satisfied, okay? Because that this is okay. And so we resolve our problem. Alright, so that is the idea around the Limberts. And so the key is that the Limberts find a suitable coordinate transformation. Okay, and it's very simple, just linear transformation, right? So this idea has been generalized to semi-linear partial differential equations of second order. Okay, so let's just take a short break, and then I would like to demonstrate how to generalize the Lambert's idea to the semi-linear problems, and so that we can transform the original PDF into PDE into simpler PDE. We call canonical form or normal form. Okay, right. So this